Hello, everyone, and welcome to Midnight Mind. I'm so glad you're here with me tonight. Maybe the day felt long. Your thoughts are still turning, just a little, like pages you can't quite close. Maybe you're simply someone who finds peace in quiet voices and faraway places, stories that help the world grow softer around the edges. Whatever brought you here, you're welcome. This is your time now. There's nothing to figure out. Just let yourself settle, the way snow settles on a mountainside, silent and slow. Let your breathing find its own rhythm. Let your body sink a little deeper into rest. Tonight, we're going somewhere cold and beautiful, somewhere ancient and still. We're traveling to the world of glaciers. If you drift away before the end, that's exactly where you're meant to be. Let's begin. Though they appear solid and still, glaciers are always moving. They flow downhill under the weight of their own mass, bending and creeping forward just a few centimeters each day, sometimes a few meters each year. This movement is so slow it's invisible to the human eye, but over decades and centuries, it reshapes entire valleys. The ice doesn't melt to move. It deforms like thick honey or cold plastic, responding to gravity and pressure. In some places, glaciers surge forward suddenly, traveling kilometers in just months. But most of the time, they are patient travelers, ancient rivers frozen in time, carving the land with the quiet, unstoppable force of ice. Most of the fresh water on Earth is not in lakes or rivers. It's locked away in glaciers and ice sheets, frozen and still. If all the glaciers in the world melted, sea levels would rise by more than 60 meters, enough to flood coastlines and reshape continents. This frozen water has been stored for thousands, sometimes millions of years, preserved in layers that record the climate of ages past. Glaciers are not just ice, they are reservoirs, holding water that fell as snow long before cities were built, before humans ever walked the earth. In their cold embrace, the planet's fresh water waits, silent and enormous, a resource both precious and fragile. A glacier begins as snow. Each winter, snow falls and accumulates, and if it doesn't melt completely in summer, it begins to build up. Year after year, layer upon layer, the snow piles higher. Under its own weight, the snow compresses. Air is squeezed out. The delicate crystals of fresh snow transform into dense, granular ice called firn. Over decades, sometimes centuries, the firn continues to compress until it becomes solid glacial ice, smooth and blue. This process is slow, patient, and silent. A glacier is not made in a season. It is made over lifetimes, each layer a page in a frozen book, each year a line written in ice. When you look at a glacier, especially one that has calved into the sea, you might notice a brilliant, almost electric blue. This isn't paint or a trick of the light. It's the result of how ice interacts with sunlight. As snow compresses into glacial ice, air bubbles are forced out, creating dense, pure ice. When sunlight enters this ice, the longer wavelengths, the reds and yellows, are absorbed. The shorter wavelengths, the blues, are scattered and reflected back to our eyes. The denser the ice, the deeper the blue. It's the same reason the ocean looks blue, but concentrated, frozen, glowing softly in the heart of ancient ice. Though glaciers feel remote and rare, they cover a vast area of the planet. From the ice sheets of Antarctica and Greenland to mountain glaciers in the Alps, Andes, Himalayas, and Rockies, glaciers shape the land across every continent except Australia. Antarctica alone holds about 90% of the world's ice. Greenland holds most of the rest. Together, these frozen expanses influence global weather patterns, sea levels, and ecosystems far beyond their icy borders. Glaciers are not isolated curiosities. They are part of Earth's living system, breathing slowly, responding to the rhythms of climate, and holding within them the power to change the world. Like a river, a glacier flows fastest at its center and slowest along its edges. This is because the sides of the glacier drag against the valley walls, creating friction that slows the ice. The middle, free from this resistance, moves more quickly. Over time, this difference in speed creates cracks and crevasses along the surface, especially where the glacier bends or flows over uneven ground. These cracks can be deep, sometimes reaching down hundreds of meters. Walking on a glacier is dangerous not because the ice is weak, but because it is moving, shifting, fracturing in ways invisible from above. The glacier flows like frozen water, patient and relentless. As a glacier flows over uneven terrain or around curves, tension builds in the ice. The surface, brittle and rigid, cannot bend smoothly. It cracks. These cracks, called crevasses, can be narrow or wide, shallow or deep, sometimes plunging more than 30 meters into the ice. Many are hidden under fresh snow, creating invisible traps for those who walk across the glacier's surface. Inside a crevasse, the walls glow blue, smooth and cold, carved by the slow movement of ice. They are beautiful and deadly, reminders that glaciers, though ancient and slow, are alive with motion, constantly reshaping themselves as they crawl down the mountain. The ice you see on the surface of a glacier may have fallen as snow just a few years ago, but deep inside, near the base, the ice can be thousands, even hundreds of thousands of years old. In Antarctica, some ice cores have revealed ice that formed over 800,000 years ago. This ancient ice has been compressed, buried, and preserved, moving slowly downward and outward over millennia. It holds within it bubbles of air from the atmosphere of ancient times, a frozen snapshot of the world as it was long before recorded history. Glaciers are not just ice, they are time itself, frozen and layered, waiting to tell their story. The Antarctic ice sheet is vast beyond imagination. It covers an area larger than the United States and Mexico combined, holding about 26.5 million cubic kilometers of ice. If it melted completely, global sea levels would rise by nearly 60 meters. The ice is thick, averaging over 2 kilometers in depth, and in some places reaching nearly 5 kilometers. Beneath this frozen expanse lie mountains, valleys, and even lakes. Antarctica is not just a continent of ice, it is a world buried, silent, and ancient, shaped by forces we are only beginning to understand. The ice sheet breathes slowly, growing and shrinking with the seasons, holding the planet's climate in its frozen grip. When a glacier flows through a mountain valley, it doesn't just fill the space, it carves it. The immense weight and slow movement of the ice erode the valley floor and walls, grinding them smooth and wide. Over thousands of years, a narrow V-shaped river valley transforms into a broad, U-shaped glacial valley. The sides become steep and smooth, the floor becomes flat and wide. When the glacier eventually retreats, it leaves behind a landscape sculpted by ice, recognizable and distinct. Valleys like Yosemite in California and many in the Swiss Alps were shaped this way, their dramatic cliffs and wide floors testament to the patient, unstoppable power of glaciers. When a glacier reaches the ocean or a lake, its front edge, called the terminus, begins to crack and break apart. Large chunks of ice calve off, falling into the water with thunderous crashes and towering splashes. These floating pieces are icebergs. They drift away, carried by currents and wind, sometimes traveling thousands of kilometers before melting completely. Most of an iceberg's mass is hidden underwater, only about 10% visible above the surface. They are fragments of ancient glaciers floating slowly through the sea, silent travelers carrying the cold breath of distant mountains into warmer waters where they slowly, inevitably disappear. If you stand quietly near a glacier, you might hear it. Not silence, but sound. The ice groans and creaks as it shifts. Cracks snap like gunfire. Meltwater trickles and gurgles beneath the surface. Sometimes deep booms echo across the ice as large sections break away or settle. These sounds are the glacier speaking, the voice of ancient ice under pressure, bending, breaking, and flowing. It is a strange, eerie music, beautiful and unsettling, a reminder that glaciers are not dead stone but living structures, moving and breathing in their own slow, frozen way. To listen to a glacier is to hear the planet at work. Trapped within glacier ice are tiny bubbles of ancient air, pockets of atmosphere from thousands of years ago. Scientists drill deep into glaciers, extracting long cores of ice that reveal layer upon layer of history. By analyzing the gas composition in these bubbles, they can reconstruct past temperatures, atmospheric carbon dioxide levels, and even volcanic eruptions. Dust, pollen, and ash are also preserved, offering clues about vegetation, wind patterns, and major geological events. Glaciers are more than frozen water. They are libraries, recording the story of the Earth in a language written in ice, waiting patiently to be read and understood by those willing to listen. Stretching over 400 kilometers long and up to 100 kilometers wide, the Lambert Glacier is a giant among giants. It flows from the interior of Antarctica toward the coast, draining a vast area of the ice sheet. Its sheer size is difficult to comprehend. It moves slowly, as all glaciers do, but the volume of ice it carries is staggering. The Lambert Glacier is not just large, it is a force, a conveyor belt of ancient ice moving steadily toward the sea. It reminds us that even in the coldest, most remote places on Earth, ice is always in motion, always shaping the land, always responding to gravity and time. As a glacier moves, it grinds against the bedrock beneath it, crushing and pulverizing stone into a fine, flour-like powder. This powder, called glacial flour, is so fine that it stays suspended in meltwater, giving glacial rivers and lakes a distinctive milky turquoise color. The particles scatter light in a way that makes the water glow with an otherworldly beauty. Lakes fed by glaciers often shimmer with this pale blue-green hue, a color that seems almost unnatural, too bright, too pure. But it is entirely natural, the result of rock ground to dust by the slow, patient power of ice moving over stone. Glaciers are sensitive to changes in temperature and snowfall. When more snow falls in winter than melts in summer, the glacier grows, advancing slowly down the valley. When melting exceeds snowfall, the glacier shrinks, retreating back up the mountain. This balance, called the glacier's mass balance, is delicate. Over the past century, most glaciers around the world have been retreating, losing mass as temperatures rise. Some glaciers that once reached the sea now end high in mountain valleys. The retreat is visible, measurable, and accelerating. Glaciers are not static. They respond to the world around them, breathing in and out with the rhythms of climate. When a glacier flows off land and onto the surface of the ocean, it doesn't immediately break apart. Instead, it spreads out, forming a floating platform of ice called an ice shelf. These shelves can be enormous, extending hundreds of kilometers from the coast. The Ross Ice Shelf in Antarctica, for example, is roughly the size of France. Ice shelves are still connected to the glacier on land, but they float on the sea, held in place by bays and islands. They act as buffers, slowing the flow of ice from the land into the ocean. When ice shelves collapse, the glaciers behind them can accelerate, pouring more ice into the sea and raising sea levels. In places like Greenland and Antarctica, glacial ice is not just deep, it is profound. The ice sheets covering these regions average around 2 kilometers in thickness and in some places reach nearly 5 kilometers. That's over 3 miles of ice pressing down on the bedrock below. The weight is immense, enough to depress the Earth's crust, pushing it down into the mantle. If the ice melted, the land would slowly rebound, rising over thousands of years. This ice is not a thin layer, it is a massive frozen ocean resting on solid ground, holding within it the weight and memory of ages. Fjords are narrow, deep inlets with steep cliffs, found in places like Norway, New Zealand, and Alaska. They were carved by glaciers that once flowed down mountain valleys to the sea. As the glaciers moved, they eroded the valley floor far below sea level, gouging out deep channels. When the glaciers retreated and sea levels rose, the ocean flooded these valleys, creating the dramatic, steep-walled fjords we see today. The water in fjords is often incredibly deep, sometimes over a kilometer, and the cliffs rise steeply on either side. Fjords are glacial scars, beautiful and haunting, shaped by ice that is no longer there. High in the mountains, glaciers slowly melt, especially in summer. This meltwater trickles down slopes, gathering into streams and rivers that flow into valleys below. For many communities, especially in regions like the Himalayas, Andes, and Alps, glacial meltwater is the primary source of fresh water. It fills reservoirs, irrigates crops, and sustains ecosystems. But as glaciers shrink, this water source becomes less reliable. Rivers that once flowed year-round may run dry in summer. Millions of people depend on glaciers they will never see, on ice that is quietly disappearing. The future of water in many parts of the world is tied directly to the fate of glaciers. Beneath a glacier, where ice meets rock, there is often a thin layer of water. This water, created by pressure and friction, acts like a lubricant, allowing the glacier to slide more easily over the bedrock. This process is called basal sliding, and it's one of the main ways glaciers move. The warmer the base of the glacier, the more water there is, and the faster the glacier can flow. In some glaciers, especially in warmer climates, basal sliding accounts for most of the movement. The glacier glides forward, slipping on a film of meltwater, silent and steady, like a massive ship sliding slowly down a tilted plain. Not all glaciers are vast ice sheets. Many are alpine glaciers, smaller rivers of ice nestled in high mountain valleys. They are found in the Alps, the Rockies, the Andes, the Himalayas, and many other ranges. These glaciers begin in high basins where snow accumulates and compresses over time. They flow downhill, carving valleys and creating stunning landscapes. Alpine glaciers are more accessible than polar ice sheets, and many are popular destinations for climbers and tourists. But they are also more vulnerable to warming. Many alpine glaciers have retreated dramatically in recent decades, leaving behind bare rock and shrinking ice fields, silent witnesses to a changing climate. In the coldest regions of the planet, glaciers exist in a state of near-permanent cold. Snowfall replenishes what little melts, and the ice accumulates year after year, century after century. Some glaciers in Antarctica and Greenland have existed for hundreds of thousands of years, continuously growing and flowing. They are among the oldest continuous ice formations on Earth. To stand on such a glacier is to stand on ice that fell as snow long before human civilization began, before agriculture, before language. These glaciers are time made visible, frozen and patient, enduring through ages we can barely imagine. When snow falls and compresses into ice, tiny pockets of air are trapped within it. These bubbles are sealed away, preserved as the ice continues to accumulate above them. Scientists drilling into glaciers can extract these bubbles and analyze the air inside. It's like opening a time capsule. The air reveals the composition of the atmosphere at the time the snow fell, including levels of carbon dioxide, methane, and other gases. This allows researchers to reconstruct past climates with remarkable precision. The bubbles are small, almost invisible, but they hold immense value, tiny windows into the Earth's ancient atmosphere, frozen and waiting. Across the world, glaciers are retreating. Measurements taken over the past century show that the rate of melting has accelerated dramatically, especially in the last few decades. Glaciers that once extended deep into valleys now end high on mountain slopes. Ice shelves that were stable for thousands of years are collapsing. The cause is clear. Rising global temperatures, driven by increased greenhouse gases, are warming the planet faster than glaciers can adapt. The ice is responding, melting, thinning, disappearing. What took thousands of years to build is being lost in decades. The glaciers are speaking, and their message is urgent. During warmer months, the surface of some glaciers becomes dotted with bright blue lakes. These are supraglacial lakes, pools of meltwater that collect in depressions on the ice. They can be small or large, shallow or surprisingly deep. The water is incredibly cold and often stunningly clear. These lakes absorb more heat than white ice, which accelerates melting. Sometimes the water drains suddenly through cracks in the glacier, disappearing into the ice below in cascading waterfalls. These surface lakes are temporary, ephemeral features, appearing in summer and freezing over in winter, but they are beautiful, glowing jewels on the glacier's ancient, cracked surface. When a massive section of a glacier breaks away and falls into the sea, it doesn't just make noise, it creates seismic waves, vibrations that can be detected by instruments thousands of kilometers away. These are called glacial earthquakes or icequakes. They occur most often in Greenland and Antarctica, where large glaciers calve enormous icebergs into the ocean. The impact is sudden and violent, the equivalent of a small earthquake. The glacier shakes, the ground trembles, and the ice, freed from its frozen prison, crashes into the water with a force that echoes across the ice and through the earth itself. While most glaciers around the world are retreating, the Perito Moreno Glacier in Patagonia continues to advance. It pushes forward, calving massive chunks of ice into the lake below with thunderous roars. Scientists aren't entirely sure why this glacier behaves differently, but it may be related to its unique geometry and local climate conditions. The Perito Moreno is a rare exception, a reminder that glaciers are complex systems influenced by many factors. Its advance is slow but steady, a frozen river that refuses to retreat, still carving the land as glaciers have done for thousands of years. High in the mountains, where snow accumulates in sheltered basins, glaciers begin to form. As the ice grows and flows downhill, it carves into the rock, eroding the back and sides of the basin into a steep, bowl-shaped depression called a cirque. These cirques are smooth and rounded, often with steep walls and a flat floor. When the glacier melts, it leaves behind a small lake called a tarn, nestled in the cirque. These features dot mountain landscapes around the world, quiet reminders of glaciers that once filled valleys but have since retreated, leaving only their sculptural mark on the stone. As a glacier moves, it scrapes up soil, rocks, and boulders, carrying them along like a conveyor belt. When the glacier melts, this material is deposited in piles and layers called glacial till. Till is unsorted, meaning large boulders sit next to fine clay, all mixed together. This chaotic jumble is different from sediment deposited by water, which sorts particles by size. Glacial till covers large areas of land in regions once covered by ice sheets, shaping the soil and landscape. It's the glacier's signature, a geological fingerprint left behind, marking where the ice once rested and moved. Sometimes glaciers pick up enormous boulders and carry them for kilometers, even hundreds of kilometers, before depositing them far from their source. These are called glacial erratics. They sit alone, often on flat plains or hilltops, looking out of place because they are. The rock type doesn't match the surrounding geology. Geologists use erratics to trace the path of ancient glaciers, mapping where the ice once flowed. These boulders are travelers, carried by ice across landscapes, silent witnesses to the power and reach of glaciers that moved continents of stone, one slow meter at a time. Covering about 1.7 million square kilometers, the Greenland ice sheet is second only to Antarctica. It holds enough ice to raise global sea levels by more than 7 meters if it melted completely. The ice is thick, averaging around 2 kilometers in depth. In recent years, Greenland has been losing ice at an accelerating rate, with meltwater flowing into the ocean and contributing to sea level rise. The ice sheet is ancient, some parts over 100,000 years old, but it is responding rapidly to warming temperatures. Greenland's ice is not just a frozen landscape, it's a reservoir, a climate regulator, and a warning. As a glacier moves, it pushes and carries rock, soil, and debris along its sides and front. When the glacier retreats or melts, this material is left behind in long, winding ridges called moraines. Lateral moraines form along the sides of the glacier. Terminal moraines mark the furthest point the glacier reached. Medial moraines form when two glaciers merge, their side debris combining into a stripe down the center. These moraines are visible for centuries, long after the glacier has disappeared, like lines drawn on the landscape, marking where the ice once stood. In summer, meltwater flows over, under, and through glaciers, carving tunnels and caves into the ice. These passages can be vast cathedral-like spaces with walls of glowing blue ice and ceilings that drip with water. Exploring glacial caves is dangerous, as they can collapse or flood without warning, but they are breathtakingly beautiful. The ice inside is smooth, sculpted by flowing water into organic, flowing shapes. Light filters through the ice, turning the interior into a world of soft, shifting blues and whites. These caves are temporary, reforming each year, ephemeral chambers within the ancient ice. Ice is highly reflective, bouncing much of the sun's energy back into space rather than absorbing it. This is called albedo. Glaciers and ice sheets play a crucial role in regulating Earth's temperature by reflecting sunlight. But as glaciers melt and are replaced by darker surfaces like rock, soil, or open water, less sunlight is reflected and more is absorbed. This warms the area further, causing more melting, a feedback loop that accelerates ice loss. The shrinking of glaciers not only raises sea levels, but also reduces the planet's natural cooling system, making the world warmer still. Sometimes glaciers trap water behind natural ice dams, forming large lakes. These glacial lakes can hold enormous volumes of water. If the dam weakens or breaks, the water can burst out suddenly in a catastrophic flood called a glacial lake outburst flood, or GLOF. These floods are extremely powerful, capable of sweeping away everything in their path: villages, bridges, roads. They occur with little warning and have caused deadly disasters in the Himalayas, Andes, and other mountain regions. The water rushes down valleys with the force of a tsunami, carrying ice, boulders, and debris in a violent torrent. Glacial lakes are beautiful, but beneath their calm surfaces lies potential danger. Scientists have long been fascinated by glaciers. In the 19th century, naturalists like Louis Agassiz proposed that Earth had once been covered by vast ice sheets, an idea that revolutionized geology. Since then, glaciers have been studied intensively, measured, mapped, and monitored. Researchers drill ice cores, measure flow rates, and track changes in glacier size. This work has revealed much about Earth's climate history and the forces that shape the planet. Glaciers are not just objects of beauty. They are scientific archives, recording the past and responding to the present. Studying them helps us understand the world we live in and the changes unfolding before us. When a large piece of ice breaks off a glacier and falls into the sea or a lake, the sound is unforgettable. A deep crack echoes across the ice, followed by a thunderous crash as the iceberg hits the water. The impact sends waves rippling outward, and the water churns white with foam. The sound can be heard for kilometers, a primal, powerful noise that reverberates through the landscape. It's the sound of ice breaking free, of ancient frozen water returning to the sea. Witnessing a calving event is awe-inspiring, a reminder of the glacier's raw power and the inevitability of change. Most glaciers flow steadily, moving just a few meters per year, but some glaciers experience surges, sudden periods of rapid movement when they can travel kilometers in just months. The reasons for surging are not fully understood, but they may involve changes in basal water pressure or internal ice structure. During a surge, the glacier's surface cracks and buckles, and the ice moves with startling speed. Then, just as suddenly, the surge ends, and the glacier returns to its slow, steady pace. These surges are unpredictable, dramatic events, reminders that glaciers, though ancient, are far from static. They are dynamic, capable of sudden, powerful motion. During the last ice age, which ended about 11,700 years ago, massive ice sheets covered large parts of the northern hemisphere. The Laurentide ice sheet blanketed Canada and much of the northern United States. The Scandinavian ice sheet covered northern Europe, These ice sheets were kilometers thick and reshaped the continents they covered. They carved the Great Lakes, scoured valleys, and deposited vast amounts of sediment. When they retreated, they left behind a transformed landscape. The world we live in today, with its lakes, rivers, and rolling hills, was shaped by these ancient glaciers. The ice is gone, but its mark remains. As glaciers flow, they pick up rocks, soil, and debris from the ground beneath them. This material becomes frozen into the ice, sometimes in layers, sometimes scattered throughout. When the glacier melts, this debris is released, creating moraines, till, and erratics. But within the ice, the rocks are preserved, sometimes for thousands of years, suspended in frozen stillness. These rocks tell stories. They reveal where the glacier has been, what kind of terrain it crossed, and how it moved. The ice is not just water frozen solid. It's a carrier of history, a vessel holding pieces of the land within its cold embrace. Most glaciers move at a pace measured in centimeters per day or meters per year. Its movement so slow it's almost imperceptible, like watching a tree grow or stone erode. But this slowness is deceptive. Over centuries and millennia, glaciers reshape entire landscapes, carve mountains, and move billions of tons of rock. Their power lies not in speed, but in patience and persistence. They don't rush. They don't stop. They simply continue day after day, year after year, quietly grinding, flowing, carving, and building. In their slowness, they are unstoppable. In their patience, they are mighty. The ice in glaciers is not the same as the ice in your freezer. It's been compressed under immense pressure for years, decades, or centuries. Air bubbles have been squeezed out, and the ice has become dense, hard, and incredibly strong. It can support enormous weight and withstand forces that would shatter regular ice. Glacial ice is also crystalline, with grains that can be seen under magnification. This density is what allows glaciers to carve through rock and carry massive boulders. It's not fragile, it's ancient, compressed, and resilient, ice transformed by time and pressure into something far stronger than it began. The terminus, or snout, of a glacier is where the ice meets its end. In some glaciers, the snout rests on land, slowly melting and depositing sediment. In others, it reaches the sea or a lake, where chunks break off and float away as icebergs. The position of the snout changes over time. If the glacier is advancing, the snout moves forward. If it's retreating, the snout pulls back up the valley. Scientists monitor the snout closely because its position is a clear indicator of the glacier's health. A retreating snout means the glacier is losing mass, a visible, measurable sign of change. Sometimes a glacier blocks a valley or river, creating a natural dam. Water builds up behind it, forming a glacial lake. These dams can be stable for years, but they are made of ice, and ice is vulnerable to melting and cracking. If the dam fails, the water rushes out in a sudden, catastrophic flood. These glacial outburst floods, or Jökulhlaups, are common in places like Iceland, where volcanic heat beneath the ice can melt the dam from below. The floods are powerful and destructive, sweeping away everything in their path. Glaciers don't just hold ice. Sometimes they hold back the sea until the moment they can't. Not all glaciers are pristine white. Some are covered with dark ash, volcanic debris, or rock dust, giving them a blackened appearance. These are often called dirty glaciers or black glaciers. The dark surface absorbs more heat from the sun, which can accelerate melting. In places like Iceland and Alaska, volcanic eruptions coat nearby glaciers in ash, turning them gray or black. The contrast is striking, a dark river of ice winding through the mountains, stained by fire and dust. These glaciers remind us that ice and fire can coexist, that the frozen and the molten are sometimes neighbors, shaping the land in tandem. When a small tributary glacier flows into a larger main glacier, it often enters at a higher elevation. The main glacier, being more powerful, erodes its valley deeper and faster. When both glaciers retreat, the tributary valley is left hanging high above the main valley floor. Water from the hanging valley often forms waterfalls that plunge dramatically down to the valley below. These hanging valleys are common in glaciated mountain regions and create some of the most stunning landscapes on Earth. They are scars of ice, places where two glaciers once met and where water now falls freely, tracing the path the ice once carved. Glaciers are natural freezers. Anything trapped within them is preserved, sometimes for thousands of years. Archaeologists have found ancient tools, clothing, and even human remains frozen in glacial ice. The famous Iceman, Ötzi, was found in the Alps, preserved in ice for over 5,000 years. Scientists have also discovered ancient plants, pollen, and even microorganisms frozen in glacial layers. As glaciers melt, these treasures are revealed, offering rare glimpses into the past, but they also decay quickly once exposed to air and warmth. The ice holds history, but only as long as it remains frozen. As a glacier moves over bedrock, the rocks and debris frozen in its base act like sandpaper, scratching and scoring the surface. These scratches, called glacial striations, are often parallel and can be several meters long. They show the direction the glacier was moving and are visible long after the ice has melted. Geologists use striations to map ancient glaciers and understand their flow patterns. These scratches are the glacier's signature, etched into stone, a record of passage, of weight, and of time. The ice may be gone, but its mark remains, written in lines across the rock. When a piece of a glacier breaks off into the ocean, it becomes an iceberg. These floating chunks of ice can be enormous, some the size of small islands. They drift with ocean currents, slowly melting as they move into warmer waters. Some icebergs can float for years, traveling thousands of kilometers before disappearing entirely. The largest icebergs come from Antarctica, where massive tabular bergs break off from ice shelves. These icebergs are flat-topped, stark, and imposing, floating monuments of ancient ice drifting silently through the Southern Ocean, slowly dissolving back into the sea from which they came. Glaciers don't react to weather, only to climate. A single warm summer won't melt a glacier significantly, and a cold winter won't reverse years of melting. Glaciers respond to long-term trends, accumulating changes over decades. This makes them excellent indicators of climate, but it also means their response is delayed. Even if warming stopped today, many glaciers would continue to retreat for years or decades, responding to changes already set in motion. The ice has memory. It holds on to the past and carries it forward. What we see today in glacier retreat is the result of decades of warming, and what happens next depends on what we do now. The word glacier traces its roots to the Latin word glacies, meaning ice. It passed through French, where glacier referred to ice or a place of ice before entering English. The name is simple and direct: ice that moves, ice that shapes the land. Languages around the world have their own words for glaciers, reflecting the different relationships cultures have with ice. In Icelandic, jökull means glacier. In Tibetan, gangs means snow or ice mountain. But whatever the word, the concept is the same: rivers of ancient ice, patient and powerful, carving their way through the world. Though solid, glaciers behave like very slow-moving fluids. When a glacier encounters an obstacle, like a mountain or large rock, it doesn't stop. It flows around it, bending and deforming to fit the shape of the land. The ice compresses on the uphill side and stretches on the downhill side, creating pressure and tension. This movement can crack the surface, forming crevasses, but the glacier keeps moving, adapting its shape to the terrain, flowing like frozen water through the landscape. It's a testament to the strange nature of ice under pressure, both solid and flowing, rigid and flexible, stone and river all at once. By studying how glaciers are changing today, scientists can model what might happen in the future. They measure ice loss, track glacier movement, and monitor meltwater flow. This data is fed into computer models that simulate how glaciers will respond to continued warming. The results are sobering. If current trends continue, Many glaciers will disappear entirely within this century, and ice sheets in Greenland and Antarctica could contribute significantly to sea level rise. Glaciers are not just indicators of past climate. They are predictors of the future, showing us in real time what happens when the world warms and what that means for coastlines, cities, and people. When you look at the cross-section of a glacier, especially in a crevasse or at the edge of an iceberg, you might see alternating bands of blue and white ice. The white bands are formed from snow that still contains air bubbles, making them opaque. The blue bands are older, denser ice where the air has been compressed out, allowing light to penetrate and scatter. These layers are like pages in a book, each one representing a different time, a different snowfall, a different year. The banding is beautiful, a natural art created by time, pressure, and the slow transformation of snow into ancient ice. You don't have to travel to the poles to find glaciers. High mountains near the equator, like Mount Kilimanjaro in Tanzania and the Andes in Ecuador, have glaciers at their peaks. At these high altitudes, temperatures are cold enough for snow to accumulate and compress into ice, even in the tropics. But these glaciers are especially vulnerable to warming. Many have retreated dramatically in recent decades, and some are expected to disappear entirely within years. They are the canaries in the coal mine, the first to respond to warming temperatures, isolated and fragile, clinging to the highest peaks in a warming world. Cold, dense air over a glacier sinks and flows downhill, creating powerful winds called katabatic winds. These winds can be sudden and strong, rushing down glacial valleys with surprising force. In places like Antarctica and Greenland, katabatic winds can reach hurricane strength, carrying snow and ice with them. They make the already frigid environment even colder, and they shape the landscape, eroding snow and sculpting ice. These winds are the glacier's breath, the cold exhalation of ancient ice flowing down the mountain. A reminder that glaciers don't just shape the land, they shape the air, the weather, and the world around them. If you gathered all the water flowing in all the rivers on Earth and added all the water in all the lakes, it would still be less than the amount of fresh water locked in glaciers and ice sheets. Glaciers are the planet's largest reservoir of fresh water, holding it in frozen storage for thousands of years. This water is essential not just for the present, but for the future. As glaciers melt, they release this stored water, initially increasing river flow, but eventually leading to shortages as the ice disappears. The water in glaciers is not infinite. It's a reserve built over millennia and now being spent far faster than it was saved. The weight of a glacier is immense, pressing down on the Earth's crust with tremendous force. Over time, this weight causes the land to sink, a process called glacial depression. But when the glacier melts and the weight is removed, the land slowly rebounds, rising back up. This is called glacial isostatic adjustment, and it can take thousands of years. In places like Scandinavia and Canada, the land is still rising, even though the ice sheets that once covered them melted over 10,000 years ago. The Earth remembers the weight of the ice and is still recovering, slowly lifting, adjusting, healing from the pressure. When a volcano erupts near a glacier, ash can fall onto the ice, creating a dark layer that gets buried by subsequent snowfall. Over time, this ash layer becomes a marker, a visible line in the glacier's stratigraphy. Scientists use these ash layers to date the ice and correlate it with known volcanic eruptions. The ash acts like a timestamp, a moment frozen in the ice. It also tells the story of the land around the glacier, of mountains that erupted, of skies that darkened, of ash that drifted down onto the snow and was buried, layer by layer, in the slow accumulation of time. In summer, when the sun warms the glacier's surface, meltwater begins to flow. It trickles down cracks, gathers into streams, and carves channels through the ice. The sound is constant, a soft symphony of dripping, gurgling, and rushing water. It's the sound of ice transforming back into liquid, of ancient snow returning to the hydrological cycle. Standing on a glacier in summer, you can hear it breathing, sighing, releasing the water it has held for so long. It's a sound both beautiful and melancholy, the glacier letting go, one drop at a time, melting into memory. Long after a glacier has melted and disappeared, its influence remains. The valleys it carved, the moraines it left, the lakes it formed, all persist. Glacial landscapes are distinctive, recognizable, marked by smooth bedrock, U-shaped valleys, and scattered boulders. These features shape ecosystems, water flow, and human settlement patterns. The ice may be gone, but its legacy is written into the land. You can walk through a valley carved by a glacier that melted 10,000 years ago and still see its fingerprints. The glacier shaped the earth, and the earth remembers, long after the ice has turned to water and flowed away. In rare cases, glaciers can harbor tiny organisms, algae, bacteria, and fungi that live in the meltwater and on the ice surface. Some of these organisms are bioluminescent, capable of producing light. On very dark nights, if conditions are right, a glacier might glow faintly with this soft, eerie light. It's a rare and magical sight, the ice glowing from within, lit not by the sun or stars, but by life itself. These organisms survive in one of the harshest environments on Earth, clinging to existence in the cold, and in doing so, they add a shimmer of life to the ancient frozen world of the glacier. On the surface of some glaciers, small depressions form, filled with dark sediment, dust, and microorganisms. These are cryoconite holes, tiny ecosystems existing on the ice. The dark material absorbs heat, melting the ice beneath it and creating small pools. Within these pools, algae, bacteria, and even tiny invertebrates live and reproduce. These ecosystems are isolated, unique, and surprisingly diverse. They show that life can find a foothold even in the most unlikely places, even on the surface of a glacier, in pools of meltwater just centimeters deep. Life is persistent, adaptive, and endlessly creative, thriving even on rivers of ancient ice. Layers of ash, dust, and rare isotopes in glacier ice can reveal events that shaped Earth's history. Volcanic eruptions leave ash layers. Asteroid impacts can scatter debris across the globe, some of which lands on glaciers and gets buried. By drilling ice cores and analyzing their layers, scientists can identify these events and date them precisely. The ice holds the memory of catastrophes, of skies darkened by ash, of impacts that changed the course of life on Earth. Glaciers are not just climate archives. They are witnesses to the dramatic, violent, and transformative moments that have shaped our planet. When glaciers and ice sheets melt, they release massive amounts of fresh water into the ocean. This fresh water is less dense than salty seawater, and it can affect ocean circulation patterns. In the North Atlantic, for example, melting ice from Greenland could slow the Atlantic meridional overturning circulation, a major ocean current that helps regulate climate. Changes in ocean circulation can have far-reaching effects, altering weather patterns, marine ecosystems, and even the distribution of heat around the planet. Glaciers, though they seem remote and isolated, are connected to the global system. When they change, the world changes with them. When an iceberg or a piece of glacial ice melts, tiny bubbles of ancient air trapped in the ice are released. As they escape, they make a soft crackling or fizzing sound, often described as bergy seltzer. It's the sound of air that was trapped thousands of years ago, finally being set free. Scientists and explorers who spend time near glaciers and icebergs often describe this sound with a sense of wonder. It's subtle, almost musical, a whisper from the past. The ice is releasing not just water but history, one tiny bubble at a time. In some glaciers and snowfields, especially in summer, patches of snow turn pink or red. This is caused by a type of algae called Chlamydomonas nivalis, which contains a red pigment to protect itself from UV radiation. The algae thrive in cold, sunlit conditions, blooming on the surface of the snow. The result is a striking, almost surreal landscape, fields of pink or red snow stretching across the white ice. The phenomenon is sometimes called watermelon snow because it can even smell faintly sweet. It's a reminder that life exists even here, even in the cold, adding color and vitality to the frozen world. Humans have long been fascinated by glaciers. They appear in myths as the homes of gods or giants, in literature as symbols of the sublime and the eternal, and in art as subjects of awe and beauty. Romantic painters like Caspar David Friedrich depicted glaciers as places of mystery and grandeur. Explorers wrote of them with reverence and fear. Indigenous peoples living near glaciers wove them into their stories and spiritual beliefs. Glaciers are more than geological features. They are part of the human imagination, symbols of nature's power, beauty, and indifference. They inspire, terrify, and humble us, reminding us of forces far greater than ourselves. Glaciers are retreating, ice is melting, the changes are visible, measurable, and accelerating. But the future is not yet written. The rate at which glaciers continue to shrink, or whether some can stabilize or even grow again, depends on global efforts to address climate change. Reducing greenhouse gas emissions, protecting natural systems, and adapting to changes already underway can make a difference. Glaciers have survived for thousands of years through ice ages and warm periods, but they have never faced change this fast. What happens next is up to us. The ice is speaking. The question is whether we will listen. Deep inside some glaciers, flowing meltwater carves tunnels and chambers, creating ice caves of stunning beauty. The walls are smooth and sculpted, glowing with an ethereal blue light as sunlight filters through the dense ice. These caves are temporary, reforming each year as water flows and refreezes. Exploring them is dangerous, as the ice can shift, crack, or collapse without warning. But for those who venture inside, the experience is otherworldly. The air is cold and still, the light is soft and otherworldly. It's like stepping into the heart of the glacier itself, a hidden world of frozen beauty, ancient and fleeting. When a glacier flows over a steep drop or cliff, the ice doesn't flow smoothly. Instead, it fractures and tumbles, creating a chaotic jumble of ice blocks called an icefall. These areas are extremely dangerous, with constantly shifting ice, deep crevasses, and frequent avalanches. Climbers attempting to summit peaks like Mount Everest must navigate treacherous ice falls, where the ice is always moving, always unstable. Ice falls are dramatic and beautiful, rivers of ice frozen mid-cascade, but they are also reminders of the glacier's relentless, unpredictable power, constantly breaking and reforming as it flows downhill. Within the layers of glacial ice, scientists have found pollen grains preserved for thousands of years. These microscopic grains traveled on the wind, landed on the glacier's surface, and were buried by subsequent snowfall. By extracting and analyzing these pollen grains, researchers can reconstruct what plants were growing in the region at different times. This reveals how ecosystems changed, how forests expanded or retreated, and how climate shifts affected vegetation. The glacier holds not just ice, but the memory of forests long gone, meadows that bloomed thousands of years ago, locked in frozen stillness. The immense pressure and friction of a glacier moving over bedrock can cause small earthquakes known as icequakes or glacial earthquakes. These occur when the glacier suddenly shifts, breaks, or accelerates. They're usually minor, but in some cases they can be felt by people living nearby. Scientists monitor these quakes to understand glacier dynamics and predict when large calving events might occur. The ice isn't silent as it moves. It groans, cracks, and sometimes shakes the ground beneath it, a reminder that glaciers are not static monuments but living, moving, powerful forces. When a glacier advances, it can block a river valley, trapping water behind it and forming a large glacial lake. These lakes can exist for years, growing larger as more water accumulates, but the ice dam is unstable. It can melt, crack, or be undermined by water pressure. When it fails, The lake drains suddenly, releasing millions of cubic meters of water in a matter of hours. The resulting flood, called a glacial outburst flood or Jokul is devastating, capable of reshaping valleys and destroying anything in its path. These events are sudden, violent, and unpredictable. When two glaciers merge, the lateral moraines on their inner edges combine to form a medial moraine, a stripe of rock and debris running down the center of the combined glacier. Large glaciers fed by multiple tributaries can have several medial moraines, creating striking patterns visible from above. These stripes are like roads on the ice, marking the paths of different ice streams as they flow together. They tell the story of the glacier's tributaries, of smaller rivers of ice joining the main flow, carrying their rocky cargo down the mountain in parallel lines. Scientists have discovered living microorganisms in glacial ice that has been frozen for tens of thousands of years. These microbes enter a state of suspended animation, their metabolism slowed to nearly nothing, waiting for conditions to improve. When the ice melts or samples are brought to the lab and warmed, some of these microbes revive and become active again. They are survivors from a different world, a different climate, a different age. Studying them helps scientists understand the limits of life, how organisms adapt to extreme conditions, and what life might look like on frozen worlds beyond Earth. On some glaciers, small balls of moss, often called glacial mice, can be found scattered across the surface. These moss balls form around a small stone or piece of debris and grow slowly over time. They roll or shift slightly with the wind or melt water, preventing any one side from being buried or exposed to too much sun. As a result, they remain roughly spherical. Glacial mice can live for years, slowly migrating across the glacier's surface. They are strange, almost whimsical features, small oases of life moving slowly across the ancient ice. Glaciers are dynamic, constantly adjusting to seasonal changes. In winter, when snowfall exceeds melting, the glacier may advance slightly, its terminus creeping forward. In summer, when melting outpaces accumulation, the terminus retreats. This seasonal back and forth is normal, but the long-term trend, whether the glacier is growing or shrinking overall, depends on the balance over many years. Watching a glacier's terminus over time is like watching it breathe, advancing and retreating with the seasons, responding to the rhythm of the year. When glacial meltwater flows away from the terminus, it carries sediment with it, rocks, sand, and clay ground from the bedrock. As the water spreads out and slows, it deposits this sediment in layers, creating broad, flat plains called outwash plains or sand dunes. These plains can extend for kilometers beyond the glacier, forming fertile, level ground. In places like Iceland and Alaska, outwash plains are prominent features of the landscape, gray and barren near the glacier but gradually colonized by plants farther away, a transition zone between ice and life. Dust carried by wind can travel thousands of kilometers, settling on glaciers far from its source. When this dust is buried by snow, it becomes a layer within the ice, visible in ice cores as a thin, dark band. By analyzing the composition of this dust, scientists can trace its origin, sometimes to deserts on other continents. The glacier holds not just local history, but global history, capturing particles from faraway lands, blown on ancient winds, and preserved in frozen stillness. It is a silent record of the atmosphere's long journey across the planet. Over geological time, glaciers are among the most powerful erosive forces on Earth. They carve valleys, grind down peaks, and transport vast amounts of rock. Mountain ranges that have experienced repeated glaciations are often smoother, more rounded, with dramatic U-shaped valleys and sharp ridges. The Alps, the Rockies, the Himalayas all bear the marks of glacial sculpting. The mountains we see today were shaped not just by tectonic forces, but by ice, patient and relentless, grinding away stone over millions of years, one slow meter at a time. Just as trees grow rings each year, glaciers accumulate layers of snow and ice that can be counted and dated. Each winter, fresh snow falls onto the glacier's surface, light and delicate at first. As spring arrives and temperatures rise, some of that snow may melt, compacting what remains. Then summer brings warmth and the surface may melt further, leaving behind a thin layer of dust, pollen, or volcanic ash. When autumn cools and winter returns, new snow falls again, burying the previous year's layer beneath a fresh blanket of white. Over time, these annual cycles create visible bands within the ice, much like the rings inside a tree trunk. Each band represents a single year, a full cycle of seasons frozen in place. In ice cores, which scientists drill from deep within glaciers, these layers appear as distinct lines, some thick, some thin, varying in color and texture depending on how much snow fell that year and what particles were trapped within it. By counting backward through these layers, scientists can construct a timeline stretching back thousands of years. Each layer is a year, a season, a moment in time, frozen and preserved. Some layers are wide, indicating heavy snowfall. Others are narrow, marking years of drought or warmth. Some contain dark streaks of ash from volcanic eruptions, marking specific events that can be cross-referenced with historical records. Others hold bubbles of ancient air, tiny pockets of atmosphere from centuries past, offering clues about temperature, carbon dioxide levels, and even the composition of the air people once breathed. The glacier's layers are a calendar marking the passage of time in ice, a record as precise and readable as the rings in an ancient tree. They tell stories of warm years and cold ones, of droughts and storms, of eruptions and quiet decades. They hold within them the memory of the planet's climate, written in frozen bands, waiting patiently to be read by those who know how to listen. Each layer is a page in a book, and together they form a narrative stretching back through deep time, a story of Earth's changing moods, its rhythms and cycles, all preserved in the silent, patient embrace of ice. When glaciers on land melt, the water flows into rivers and eventually reaches the ocean, raising sea levels. This process is slow, gradual, and often invisible to those who live far from the ice. But it is happening steadily, year after year, as temperatures rise and glaciers shrink. Even small alpine glaciers perched high in mountain valleys far from the coast contribute to this process. The meltwater trickles down slopes, gathers into streams, and joins rivers that wind their way through valleys and plains, eventually emptying into the sea. Cumulatively, the melting of thousands of glaciers around the world adds up, contributing significantly to sea level rise. Each glacier, no matter how small, releases water that was once frozen and locked away. In places like the Himalayas, the Andes, and the Alps, glaciers that have existed for millennia are shrinking rapidly, their meltwater swelling rivers and feeding reservoirs. But this water, once released, does not return to the glacier. It flows onward, joining the global hydrological cycle and ultimately adding volume to the oceans. The ice in Greenland and Antarctica has the potential to raise sea levels by many meters if it melts completely. Greenland alone holds enough ice to raise global sea levels by more than 7 meters. Antarctica holds enough to raise them by nearly 60 meters. These are not abstract numbers. They represent coastlines redrawn, cities flooded, islands submerged, and millions of people displaced. The ice sheets are vast, ancient, and seemingly permanent, but they are not immune to warming. Already they are losing mass at an accelerating rate, shedding billions of tons of ice each year into the surrounding seas. Glaciers are not isolated from the ocean. They are connected by gravity and water, and what happens in the mountains eventually reaches the sea. A glacier melting in the Alps contributes to the same rising tide that threatens coastal cities in Asia, Africa, and the Americas. The ice in Antarctica, though thousands of kilometers from any inhabited shore, affects sea levels everywhere. The planet's water is interconnected, flowing through rivers, oceans, and ice in a continuous global cycle. When glaciers melt, the balance shifts. The frozen reservoirs empty, and the oceans rise, slowly but inexorably, reshaping the world's coasts and the lives of those who live near them. In the deepest, oldest parts of ice sheets in Antarctica and Greenland, some of the ice is over 100,000 years old, dating back to the last ice age and beyond. This ice fell as snow when the world was covered in ice, when sea levels were over 100 meters lower than they are today, when mammoths walked the earth and Neanderthals lived in Europe. It fell during a time when the climate was colder, the atmosphere different, and the landscape unrecognizable compared to what we see now. This ancient ice has been compressed, buried, and preserved beneath layer upon layer of younger snow and ice. It lies at the very bottom of the ice sheet, pressed down by the weight of kilometers of ice above it. Over tens of thousands of years it has been squeezed, compacted, and transformed, its original fluffy snowflakes now dense, clear, crystalline ice. It holds within it bubbles of air from that distant time, tiny capsules of atmosphere from a world that no longer exists. To drill into this ice is to travel back in time, to touch a world that vanished long before recorded history. Scientists who extract ice cores from these depths handle them with care and reverence, knowing that they are holding something precious, a physical connection to the past. The ice is cold, smooth, and heavy. When a sample is brought to the surface and examined, it reveals secrets. The air bubbles contain gases that show what the atmosphere was like thousands of years ago. The ice itself contains dust, pollen, and volcanic ash, clues about climate, vegetation, and major geological events. This frozen relic of a distant past is more than just ice. It is a time capsule, a library of information about the Earth's climate history. By studying these ancient layers, scientists can understand how the planet has changed, how it has responded to shifts in temperature and atmospheric composition, and what patterns have repeated over millennia. The ice remembers. It holds the memory of ice ages and warm periods, of droughts and deluges, of eruptions and calm. And though it is silent and still, it speaks to those who know how to listen, offering lessons from a time long before humans shaped the world. As glaciers melt, they expose darker surfaces, rock, soil, or water, which absorb more sunlight than white ice. This is not a minor detail. It is a critical factor in how quickly glaciers disappear. White ice reflects most of the sunlight that hits it, bouncing that energy back into space. This reflectivity, known as albedo, helps keep the glacier cool. But when the ice melts and darker surfaces are revealed, the albedo decreases. Dark rock and soil absorb heat instead of reflecting it, warming the area and accelerating further melting. This creates a feedback loop, a cycle that feeds on itself. The more ice melts, the more dark surface is exposed. The more dark surface is exposed, the more heat is absorbed. The more heat is absorbed, the faster the ice melts. And so on. This is called a positive feedback loop, though there is nothing positive about it in terms of glacier survival. It accelerates ice loss, making it harder for the glacier to recover even if temperatures stabilize. The albedo effect plays a crucial role in regulating temperature, not just for glaciers but for the entire planet. Ice-covered regions like the Arctic and Antarctic reflect a large portion of incoming solar radiation, helping to keep the Earth cool. But as these areas lose ice, they absorb more heat, which warms the planet further, which causes more ice to melt, and the cycle continues. This feedback loop is one of the reasons why polar regions are warming faster than the rest of the world, a phenomenon known as Arctic amplification. When glaciers shrink, they lose their ability to reflect sunlight, making the region warmer and hastening their own disappearance. The glacier's retreat feeds on itself, a cycle difficult to reverse once it begins. Even if warming slows or stops, the feedback mechanisms already set in motion can continue to drive ice loss for years or decades. The glacier becomes trapped in a spiral, losing mass faster than it can rebuild, retreating up the mountain or shrinking back toward the poles, leaving behind bare rock and exposed earth that soak up the sun's warmth and ensure that the ice will not return. Beneath some glaciers, especially in Antarctica, there are lakes of liquid water kept from freezing by the immense pressure of the ice above and geothermal heat from below. These subglacial lakes are among the most isolated and mysterious places on Earth. They lie beneath kilometers of solid ice, cut off from sunlight, from the atmosphere, and from most of the planet's ecosystems. They are dark, cold, and utterly silent, sealed away from the world above by a frozen ceiling that has not been breached in millions of years. The pressure from the overlying ice is so great that it lowers the freezing point of water, allowing it to remain liquid even at temperatures well below 0 degrees Celsius. In some cases, heat from the Earth's interior, from volcanic activity or geothermal vents, warms the base of the glacier, preventing the water from freezing. The result is a hidden lake, sitting in darkness beneath the ice, untouched by the changing seasons, by storms, by the rise and fall of civilizations on the surface. These subglacial lakes are not small puddles. Some are enormous. Lake Vostok in Antarctica, for example, is one of the largest lakes on Earth, roughly the size of Lake Ontario. It has been sealed beneath more than 3 kilometers of ice for at least 15 million years, isolated from the rest of the planet's biosphere. Scientists believe that similar lakes exist beneath other parts of the Antarctic ice sheet, creating a vast, hidden network of liquid water beneath the frozen continent. What makes these lakes even more fascinating is the possibility that they harbor life. Despite the extreme cold, the total darkness, and the isolation, some scientists believe that microbial life could exist in these subglacial lakes, adapted to conditions unlike anything on the surface. These organisms, if they exist, would have evolved separately from the rest of life on Earth, cut off for millions of years, surviving in one of the most extreme environments imaginable. They might feed on minerals dissolved in the water, or on organic material trapped in the ice. They might use chemical reactions rather than sunlight as an energy source. They might represent a completely unique branch of the tree of life. Scientists drill carefully into these lakes, using sterile techniques to avoid contaminating them with surface microbes. The hope is to study the organisms that survive in such extreme conditions, to understand how life can adapt, persist, and thrive in places that seem utterly inhospitable. These hidden lakes are among the most mysterious places on Earth, dark worlds beneath the ice, untouched by sunlight, waiting to reveal their secrets. They remind us that even in the coldest, most remote corners of the planet, life may find a way, patient, resilient, and endlessly surprising. As a glacier moves over bedrock, the fine sediment embedded in the ice acts like sandpaper, polishing the rock to a smooth, shiny finish. This process is slow, almost imperceptibly slow, but over centuries and millennia, it transforms the surface of the bedrock. The rocks and grit frozen into the base of the glacier grind against the stone beneath, wearing it down, smoothing rough edges, and creating a surface that gleams when sunlight hits it. This is called glacial polish, and it can last for thousands of years after the glacier has melted and retreated. The polished rock reflects light, creating a distinctive gleam that is unlike anything produced by water or wind erosion. It is smooth to the touch, sometimes slippery, especially when wet, and it bears the unmistakable mark of ice. In many mountainous regions, hikers and climbers encounter these smooth, polished surfaces, remnants of glaciers long gone, silent witnesses to the power and patience of ice. The polish is a signature, a mark left by the glacier's passage, as if the ice reached down and gently, patiently smoothed the stone with its slow, grinding touch. It is not just a surface feature, it is a record, a physical testament to the glacier's presence, to the immense weight and pressure it exerted, to the time it spent moving over that exact spot. Geologists study glacial polish to understand how glaciers flowed, where they went, and how fast they moved. The polish can reveal the direction of ice movement, the thickness of the glacier, and even the type of rock the glacier was grinding against. In some places, the polish is accompanied by glacial striations, parallel scratches carved into the rock by larger stones dragged along by the ice. Together, these features create a landscape that tells a story, a narrative written in stone and ice, of slow, relentless movement, of grinding pressure, and of time measured not in days or years, but in centuries and millennia. The glacier may be gone, but its touch remains etched into the rock, a lasting memory of ice that once covered the land. Modern technology allows scientists to monitor glaciers with incredible precision. In the past, studying glaciers required painstaking fieldwork, climbing to remote locations, measuring by hand, and recording observations in notebooks. Today, technology has transformed how we study ice. Satellites orbit the Earth, taking high-resolution images of glaciers from space, measuring changes in their size, surface elevation, and movement with astonishing accuracy. These images can be compared over time, revealing how glaciers are growing or shrinking, where they are thinning, and how fast they are retreating. GPS devices placed on the ice track how fast and in what direction the glacier flows. These instruments, powered by solar panels and built to withstand extreme cold, send data back to researchers in real time, allowing them to monitor the glacier's movement day by day, hour by hour. Some glaciers move just a few centimeters per day, while others, during surges, can move several meters. The GPS data captures all of this, creating a detailed picture of the glacier's behavior. Drones fly over glaciers, capturing detailed maps and three-dimensional models of the ice surface. These aerial surveys can reveal features invisible from the ground, such as crevasses, meltwater channels, and changes in ice thickness. Drones can access areas too dangerous for humans, flying over unstable ice or steep terrain, gathering data that would otherwise be impossible to obtain. This data helps researchers understand how glaciers are responding to climate change in real time. They can see which glaciers are melting fastest, which are holding steady, and which, if any, are advancing. They can measure how much ice is being lost each year, how much meltwater is flowing into rivers and oceans, and how these changes are affecting ecosystems and communities downstream. The technology is advanced, sophisticated, and powerful, but the goal is simple: to listen to what the glaciers are telling us, to see their changes clearly, and to understand what those changes mean for the future. The glaciers are speaking. They are telling us through their retreat, their thinning, and their accelerating melt that the climate is changing, that the world is warming, and that the balance we have known is shifting. The technology allows us to hear them more clearly than ever before, to measure their message with precision, and to respond if we choose to listen. When you stand on a glacier, you are standing on ice that may be thousands of years old. Beneath your feet, layers of compressed snow hold the memory of ancient winters, of storms that raged before cities were built, before languages were spoken, before most of human history unfolded. You are touching water that fell as snow before nations existed, before empires rose and fell, before the modern world took shape. It is a humbling thought, a reminder of how brief our lives are in the context of deep time. Glaciers are bridges to that deep time, connections to a past so distant it is hard to imagine. They hold the memory of ancient climates, of ice ages and warm periods, of a planet constantly changing, adapting, and evolving. In their frozen stillness, they remind us that the Earth is old, patient, and far larger than our brief lives. They teach humility because they have seen so much and endured so much, and yet they respond slowly but surely to the changes we are causing now. They teach wonder because to stand on a glacier is to stand on something older than civilization, older than agriculture, older than writing. It is to touch the past directly, to feel the weight of time beneath your feet. And they teach respect because glaciers are powerful, patient, and unforgiving. They do not hurry. They do not compromise. They move at their own pace, shaped by forces far greater than any human effort, by gravity, by climate, by the slow turning of the Earth through space. To visit a glacier is to step outside the rush of modern life, to stand in a place where time moves differently, where change is measured not in days or years, but in centuries and millennia. It is to remember that we are part of something much larger, that the world existed long before us and will continue long after we are gone. The glacier does not care about our plans, our schedules, our ambitions. It simply is, flowing slowly, carving the land, holding the past, responding to the present, and moving, always moving, toward an uncertain future. Glaciers are not separate from the planet. They are not isolated features, distant and detached. They are part of the Earth's breath, part of its water cycle, part of its climate system. They shape the land, carving valleys and sculpting mountains. They feed the rivers, releasing meltwater that flows through ecosystems, nourishes forests, and sustains communities. They regulate the temperature, reflecting sunlight and cooling the planet, acting as natural thermostats that help maintain the delicate balance of the climate. They hold the past, storing ancient air, dust, and pollen in their frozen layers, preserving the story of the Earth's changing climate over thousands of years. And they influence the future, responding to warming temperatures, melting into rivers and oceans, raising sea levels and altering ecosystems in ways we are only beginning to understand. They respond to the sun, absorbing its warmth in summer and growing in winter. They respond to the atmosphere, capturing particles and gases that fall onto their surface. They respond to the ocean, calving icebergs and releasing fresh water into the sea, influencing currents and weather patterns far beyond their icy edges. Glaciers move in slow, ancient rhythms that have shaped continents and life itself. They have carved the landscapes we live in, created the soils we farm, and filled the lakes we drink from. They have influenced the evolution of species, opening and closing pathways for migration, creating refuges and barriers, shaping the distribution of life across the planet. They are not just ice. They are part of the living, breathing, constantly changing system that is the Earth. To study glaciers is to study the Earth, to understand how they form, how they move, how they respond to climate, is to understand how the planet works, how its systems are interconnected, how changes in one place ripple through the entire system. And to protect them is to protect the balance that sustains us all. Glaciers are not luxury items, optional features of a beautiful planet. They are essential, integral, woven into the fabric of the Earth's climate, water, and life. Their story is our story, written in ice, flowing through time, and still unfolding. What happens to the glaciers affects us all, whether we live in the mountains or by the sea, whether we have ever seen a glacier or only heard of them in stories. The meltwater from the Himalayas waters crops that feed millions. The ice in Greenland affects sea levels that threaten coastal cities around the world. The glaciers in Antarctica help regulate the planet's temperature, keeping the world cooler than it would otherwise be. Their fate is tied to ours. If we allow them to melt, we lose more than ice. We lose the balance they provide, the water they store, the climate regulation they offer, and the history they preserve. But if we act, if we slow the warming, reduce emissions, and protect the systems that sustain them, we give them and ourselves a chance. The glaciers are still here. They are still moving, still carving, still holding the memory of the world. And their story, our story, is still being written, one slow, patient layer at a time. And now, as the final story fades into the quiet, let the glacier rest in your mind. Let its slow, patient movement carry you gently into sleep. There's no need to hold on to anything, no need to remember. Just let the images drift, soft and weightless, like snowflakes settling on a winter morning. We've traveled together tonight, not with hurried steps or racing thoughts, but slowly, gently, the way glaciers themselves move through the world. We've walked across ice older than memory, ice that has been forming, compressing, and flowing for thousands of years. We've traced the edges of valleys carved by ancient rivers of frozen water, valleys that were shaped not in days or years, but over millennia, one patient scrape at a time. We've listened in our imagination to the sounds of the glacier, the creak of shifting ice, deep and resonant, like the groan of an old wooden ship settling in calm waters. The whisper of meltwater trickling through hidden channels beneath the surface, carving its way through the frozen world in delicate, persistent streams. The distant thunder of calving bergs, massive chunks of ice breaking free and crashing into the sea, sending waves rippling outward and echoes bouncing across the ice. These are the sounds of the glaciers speaking, the voice of deep time, slow and ancient and endlessly patient. We've stood in our imagination on surfaces that hold the history of the world in frozen layers. We've pictured ourselves looking down at ice that fell as snow before written language existed, before cities rose, before nations were drawn on maps. Beneath our feet, in those imagined moments, lay a record of the Earth's climate, its storms and calm periods, its warm years and cold ones, all preserved in bands of ice, waiting to be read like pages in a book written by the planet itself. Glaciers have been here long before us. They were here when the first humans walked the earth, and they were here long before that, carving the land, shaping mountains, filling valleys, and moving with the slow inevitability of gravity and time. They have shaped the land we live on, carved the valleys we call home, and filled the lakes we drink from. They have held the water, storing it in frozen reservoirs for centuries, releasing it slowly into rivers that nourish forests, fields, and communities far downstream. And they have recorded the past. Every layer of ice, every bubble of trapped air, every grain of dust holds information. The glaciers remember what the atmosphere was like 1,000 years ago, 10,000 years ago, even 100,000 years ago. They remember volcanic eruptions, droughts, and storms. They remember when the world was colder, when ice covered much of the northern hemisphere, and they remember the slow warming that followed, the retreat of ice, the reshaping of continents. And though they are changing, melting, retreating, they still carry within them the quiet strength of deep time. They are not gone. They are still here, still moving, still carving the land, still holding the memory of the world within their frozen layers. They are wounded, yes, they are shrinking, but they are not defeated, not yet. They endure, as they have endured for thousands of years, responding to the world around them, bending but not breaking, retreating but not disappearing entirely. You don't need to remember everything you've heard tonight. In fact, you don't need to remember anything at all. The facts, the numbers, the names of glaciers and valleys and ice sheets, they're not what matter most. What matters is the feeling, the sense of quiet awe, the reminder that the world is vast and old and full of wonders that move too slowly for us to see but shape everything we know. Just let it wash over you, soft and cool, like snow falling in the stillness. Let the stories settle gently in your mind, not as things to hold on to, but as things to rest with. Let them become part of the background, the soft murmur of the world beyond your window, the quiet knowledge that somewhere, right now, glaciers are moving, ice is forming, and the slow work of shaping the earth continues. Wherever you are, whether you're lying in bed, sitting in a chair, or resting somewhere else entirely, let your body grow heavy. Feel the weight of it, the solid, comforting weight of being held by gravity, by the earth beneath you. Let your muscles soften, let your shoulders drop, let your jaw relax, let your hands unclench, your fingers spread, your arms fall gently to your sides. Let your thoughts slow, not stopping entirely, because thoughts rarely do, but slowing, drifting, becoming less urgent, less demanding. Let them move like clouds across a calm sky, passing without effort, without resistance. If a thought rises, let it rise. If it fades, let it fade. You don't need to chase it or push it away. Just let it be and let it go. Let the ice carry you gently into rest. Picture it, if you like. A vast expanse of white, smooth, and unbroken, stretching as far as the eye can see. The surface is soft, not cold, just cool and welcoming. You're lying on it, floating on it, held safely by something ancient and solid. The ice moves beneath you, so slowly you can't feel it, but it's moving, carrying you forward, carrying you down into sleep, into the quiet depth of rest. If you're still awake, that's okay. There's no rush, there's no pressure. The glaciers will wait. They have been waiting for thousands of years. They will wait a little longer, and so will I. These words will still be here, drifting softly in the background, a gentle presence, a quiet companion as you move towards sleep in your own time, at your own pace. There's no right or wrong way to fall asleep. Some nights, sleep comes quickly, easily, like slipping into a warm pool of water. Other nights it takes longer, and that's okay too. The important thing is not to fight it, not to force it. Just let it come when it's ready. Let your body find its own rhythm, its own way down into the quiet. Thank you for being here. Thank you for spending this time with me, for letting these stories into your mind, for allowing yourself this moment of rest. In a world that so often demands speed, urgency, and constant attention, you chose to slow down. You chose to listen to stories about ice, about time, about the slow, patient forces that shape the world. That choice matters. It's a gift you've given yourself, and I hope it brings you peace. Sleep well, friend. Let the weight of the day fall away. Let the worries and plans and thoughts drift off like mist in the morning sun. Let yourself be held by the quiet, by the stillness, by the ancient, patient rhythm of the earth turning beneath you. You are safe. You are resting. You are exactly where you need to be. And somewhere, far away, a glacier is moving. Just a few centimeters today, maybe a few meters. It doesn't know you're thinking about it. It doesn't know it's being remembered, but it moves anyway, patient and unstoppable, carving its path through stone, holding the memory of the world, breathing slowly with the seasons, advancing and retreating, growing and shrinking, enduring. It has been there for thousands of years. It will be there tomorrow, and the day after that, and the day after that. It moves with the kind of patience that only ice can have, the kind of patience that comes from knowing that time is not something to fight or hurry, but something to flow with, something to surrender to. And so, as you lie here now, let yourself flow with time, let yourself surrender to it, not in defeat, but in trust. Trust that your body knows how to rest. Trust that sleep will come when it's ready. Trust that the world will still be here when you wake, and that you will be rested, renewed, ready to meet it. The glacier is still moving, the ice is still there, the world is still turning, and you, right now, are resting. You are letting go. You are drifting slowly, gently, like a snowflake falling through the air, spinning softly, catching the light, and finally, inevitably, coming to rest on the quiet, frozen surface below. Good night, friend. Sleep softly, sleep deeply. Let the glacier carry you into dreams, into stillness, into the quiet, patient embrace of sleep. You are safe. You are held. You are home. And now, let the quiet take you. Let the stillness hold you. Let the ice, ancient and patient, carry you gently, gently into rest. Good night. The words fade now, like footprints disappearing under fresh snow. The stories have been told, the journey is complete, and all that remains is the quiet, the stillness, and the soft, steady rhythm of your breathing as you drift, finally, into sleep. The glacier waits, the ice remembers, and you, dear friend, are free to rest. Sleep well, sleep long. Let the world turn without you for a while. You have earned this rest. You have walked with the glaciers. You have listened to the ice. And now, it's time to let go. Close your eyes if they're not already closed. Let your breath slow if it hasn't already. Let your mind grow quiet if it's still speaking. And let the glacier, that ancient river of ice, carry you gently, patiently into the deep, soft stillness of sleep. Good night, good rest, good dreams, and thank you truly for being here. There is nothing more to do now, nothing more to think about, nothing more to remember, just the quiet, just the stillness, just the soft, cool embrace of ice and time and rest. Let it hold you, let it carry you, let it ease you gently into sleep. The glacier is still moving, the world is still turning, and you, dear friend, are resting. Good night.